Hi, how's it going? In this video we're going to be creating a swap chain. What is a swap chain? Well, when we create a program like PyOpenGL, you know, with Pygame and everything, Pygame creates a nice kind of double buffered rendering system for us, and that's great. However, Vulkan does not have an idea of a default sort of rendering system. A rendering system, by the way, being a process for selecting an image and presenting it to the screen. For this, we must create our own. So to start with, we'll just head over to the logical device creation, and we will have to request the Swapchain. Swapchain is an extension, and it's a device level kind of extension, but that's fine. So we'll just make a list of things that we're requesting, which is just the single one here. Swapchain extension, okay, no worries, and then we'll just use that down here. So we have enabled extension count is that one there, and then enabled extension names is just device extensions. Okay, awesome, cool. So at this point, we will be requesting Swapchain capabilities. That does not mean that we've created one. So just to dig a little bit more into what a Swapchain actually is, warning, this video is going to be a little bit longer, and there is going to be a little bit more copy-paste, but hopefully it helps us understand the Vulkan environment a little bit better as well. So what I'm going to do is I'm going to create a simple class to hold all of the data fields for the support that the Swapchain has. Okay, so these are the three fundamental things we have. They're not really three because they are nested. So for instance, if we look at capabilities, then capabilities would include the number of images that the Swapchain can support, the okay, so the number of images that the Swapchain can support, the extent, so the size of images that we can support, as well as image usage and other things. Formats is basically the pixel format and the color space, and then present modes. There's a bunch of different flags for this. It's a bunch of different fundamental sort of data structures and algorithms which are used to present images to the screen. Okay, so we'll create a function which will populate that. Okay, so I've gone ahead and typed in the name of the function that I want to call to get the surface capabilities, and it's not, like, autocomplete isn't recognizing it. So to get around this, I'm going to query this. I happen to know ahead of time that this is an instance procedure address. So what I'm doing is this is querying, returning a function pointer which I can then call as if it was a regular function. By the way, we can double check this. If we control click in, then there should be, yep, up above here we have, I've said this many times, but this is a list of all the device extension functions. By the way, Swapchain, no, don't worry about that. Swapchain is a device kind of thing. As we can see here, all the Swapchain stuff, create, destroy, Swapchain images, this is all in device extension functions. So we'll be using this get device procedure address quite a lot. And then here we are, where are we? Yep, okay. And yeah, physical device surface capabilities is in an instance extension function. And so for that reason, I need to query it with this get instance procedure address. Anyway, so that's just a little quick aside. If you're having trouble, if you're writing in a function name and it's simply not recognizing it, then it's a good thing to check if it's a, you know, one of those special extension function. Okay, so let's have a bit of fun. Let's dig into what's actually in this structure. So I'm going to copy paste this. This is from the Vulkan documentation. So these are kind of all the fields that we have accessible to us inside the surface capabilities structure. So we can get the minimum image count, maximum image count, and all of these things. And I'm going to pretty much log all of these out to the console just to show. And I'm also going to, which is go to main. I'm just going to make a little dummy call here for now, just to run it. So we'll go device query Swapchain support for our instance. And we're just going to pass in true for the debug, because this isn't a real call, we're just doing it now. Okay. So to start with, let's get the minimum and maximum image count. So we can just access these as if it was a regular class. Run this now. Alrighty, so we can support a minimum of 2 images and a maximum of 8 images in our swap chain. Good to know. Okay, now let's have a look at the extent. So if we go to the extent, we have this Vulkan extent 2D, current and all of this. And this structure is a very simple structure. It literally has just 2 fields, the width and the height. So we can go ahead and print all of those. Okay, so we go support capabilities, current extent, width and height, and we do this for current, minimum, and maximum. Okay. Now, as we can see here, we created the GLFW window at a size of 640 by 480, and all of the parameters are fixed to that. Okay, fair enough. Generally, Vulkan swap chains, they're not, like, the graphics pipeline isn't really resizable that dynamically. If we resize a window, minimize, maximize, we have to recreate the whole everything, the whole swap chain graphics pipeline and all of that. That's fine. And that is the reason that this is all locked together. We then have the array layers. On that, we can only support one array layer. That makes sense. We have one window, it's one image. We're not doing any technical stuff there. And then we have, what do we have? Supported transform and current transform. Okay, so I'm going to make another helper function. I'm going to put this in the logging area. We're going to log the transforms. So we'll just go logging. Like I said, a lot of copy pasting in this video, but the reason for that is But this is just bonus stuff to kind of understand what's going on under the hood a little bit better. You can always pop into the GitHub, grab the code, have a look at it yourself, and yeah, this isn't the main functionality here, this is just bonus. Okay, so as we can see here, this is defined as a bit mask with these various bits which have been set, and they're independent of each other. So what we can do is we can perform bitwise AND operations to see if these have been set, and build this up into a list of strings and yeah, see exactly which transforms have been set here. Oh yeah, of course we do need to import that module. Okay, so as we can see here, currently we're just doing the identity transform, which is basically doing no transform at all. But we could potentially set this up so that we do our rendering as normal, and then as a final kind of whatever, before it goes to the screen, the image is rotated or flipped or something like that. Not super important, and we're not going to do that here. Next, in the interests of completeness, we can have a look at the alpha operations. Okay, so we're going to do something very similar. We'll go into logging and we'll make another helper function. And this is just basically saying if an image on the swap chain has any sort of alpha component, how are we going to handle it? So we can see this is set as another bit mask, and there are various options, and we can do bitwise and see which ones are supported. Run this here. We're just doing opaque images. Our window is not going to have any alpha on it. No alpha blending. Okay, looks good. Then we're looking at the image usage. In other words, the images which are created for the swap chain, how can they be used? So this is quite a bit. We have these flags here, and then down below we have some descriptions. I literally copy pasted these descriptions from the Vulkan specification. Okay, so as we can see, our swap chain can be the source of an image transfer. We can transfer memory to our swap chain. We can also, sorry, I'm getting that wrong. We can transfer memory from the swap chain onto other textures. So we can sample the screen, basically. Oh, sampling is a different word, isn't it? Transfer destination, so we can use it as a destination. We can blit memory directly onto the swap chain, onto the image. It can be sampled. Okay, so we can create a Vulkan image view and put that into a Vulkan descriptor slot for a sampled image or a combined image sampler, and can be sampled by a shader. Little side note here, a combined image sampler is basically an image with its own sampler together, and for a sampled image we can have images independent of sampler objects and stuff, which is pretty much the default, I would say, for unless I'm wrong there. Anyway, for OpenGL, I believe typically you have a bunch of images and then a sample. Well, it's an opaque data type, so we really don't know what's happening there. Anyway, I'm rambling. Storage. Okay, so we can use the swap chain to store general data. Color attachment. We can use it for a frame buffer or a resolve attachment. By the way, what a resolve attachment is, if we have a multi-sampled frame buffer, so it might be a 4 times or an 8 times sampling or something, the renderer does its rendering, multi-sampled rendering, but then it needs to display it on the screen, so it kind of bounces it down to a single sample frame buffer using averaging, and this step is called a resolve. And an input attachment. So what that means is, for instance, if we have something like deferred shading, you have your geometry pass and then your kind of regular pass and then your lighting pass or whatever you want to do, then that can be defined as one single pass with a number of subpasses. And we can use input to take the output of a previous subpass as the input for the next subpass, and so on. Anyway, so we have that. That's all good. And that is basically the capabilities. So then the next part that we have is the surface formats. So again, just in the interest of time, copy paste. Okay, so we get the surface formats. That's great. And then we call that function to get the formats. Okay, and here's what we have inside the surface format struct. We have the Vulkan format and the Vulkan color space, and both of these are enums, basically. They have one value. So we can go ahead and log that, and these are quite big functions. So I'm just doing it here with a dictionary and then just looking up in the dictionary, and I definitely could define the dictionary outside of the function. That's fine. I'm only going to call these functions once at creation, so that's okay. So as we can see, we can support a pixel format of basically 8 bits for red, green, blue, and alpha, and unsigned normalized values in the sRGB nonlinear color space. By the way, all these color spaces for all these formats are nonlinear sRGB. Okay, or we can have sRGB, same thing, or we can have this kind of 10-bit color format where we put 10 bits for red, green, and blue, and then the last 2 bits are for alpha. And that's it. Those are the options that we have. So in this case, I think we're going to go with the top 2, unorm and nonlinear. We don't have a choice there. Anyway, that's good. And then the last bit that we have is the present mode. So again, we query our instance for the address of the procedure, and then we call it. And I'm just going to log out this present mode, so we'll make another helper function for that. And yeah, again, the reason I'm not going too in depth in how I made these functions is they're literally just, it's an exercise of copy pasting the documentation, basically. There we have it. So these are the different options that we have. I'll go ahead and run that. Okay, so here's what we can support. We can support FIFO. Now what FIFO is we have a queue of images. So let's say our Swapchain has 2 images. We render to an image and then we say present that image. And what that does is it throws that image on a queue ready to be presented. And then we say, okay, let's render another image. So image 1 is on the queue. We can't use that, so we use image 2. Okay, we render to image 2 and then put that on the queue ready to be presented. And the issue with this is now, if it takes us some time to present, we might be about to render an image, like we're waiting to render an image, but both image 1 and 2 are on the queue, waiting to be presented. And so FIFO kind of limits the frame rate. It limits us to the refresh speed of the monitor, because that's how quickly we're presenting things. We have other options like relaxed FIFO, won't worry too much about that, mailbox and immediate. Now immediate is pretty much like no Swapchain. Like we have something, we render to it, we present it to the screen at the same time. This can cause something called vertical tearing, because we can be popping something on screen at the same time that another program is rendering to it or something. Like something bad. Bad things can happen with immediate mode. Mailbox is similar to FIFO, so we have a queue. However, the queue, where is it, is a single entry queue. So it's really just one thing. So we have image 1 and 2. We grab image 1, we render to it, then we stick it on the queue ready to present. Then, if our engine is really quick, we can grab image 2, render to it, stick that on the queue. However, that frees up image 1. It goes back onto the space that we can render to before it was presented. So this means that we can have frame rates which are not limited to the V-sync of the monitor, basically. So that's the short answer. Now, there are some cases where you do want to just limit to the frame rate. For instance, on a mobile device, there's no point running your processor as fast as possible, doing 1,000 frames per second, if you're only rendering at 60 frames per second, because that is taking up valuable battery life. On the other hand, for fun, it's good on desktop just to go as fast as possible. That's what I'm going to do, because I like it. Anyway, so that's my little spiel. Oh, by the way, important, here it says, for FIFO, it says, this is the only value of present mode that is required to be supported. So that's a good kind of fallback option if everything else fails. Good. All right, so basically we have set up our support structure, our support details. So we can get rid of that dummy call in the main function. And now we can actually start using these. Well, there's a few more support functions we need. I'm just going to copy paste these. So the first thing we need as well is we need to choose appropriate formats, present modes, and extents. Okay, so the first one, we need to choose a surface format. We have a list of formats to choose from. We'll loop through them. And like I said, I'm going to go with that 32-bit, 8-bit per channel UNORB in the sRGB nonlinear. So if we find that, we return it. If not, well, who cares? They're all valid formats. They're all supported formats. So as a default, just return the first one that we see. The next one is choosing a present mode. So again, we have a list of supported present modes. We'll loop through them. And if we see mailbox, remember that's the fast frame rate, no vertical tearing, then return that. However, if we haven't seen that, then we know at least that FIFO is supported, so we'll return FIFO. FIFO, by the way, first in, first out. Why did I not say that? Anyway. Then we need to choose the extent. So we'll request a certain width and height, and we'll check that against our capabilities. First of all, we'll create a 2D extent. As I said, an extent is a very simple structure. It just has a width and height, so that's all we need in the constructor. It's pretty much basically an array of 2 integers, width and height. Okay, so then we kind of clamp that according to what our capabilities can support, just making sure we do not exceed or go outside of the range of minimum and maximum. Okay, and now we can actually start creating the swap chain. But what I'm going to do is I'm going to create the swap chain, and I'm also going to grab a few other bits of details as well. So I'm going to kind of wrap this all up in a single class and return that class, not return the like a simple data type. So I'll make a class called Swapchain Bundle, and that will contain all the data that I want to return. Okay, so here it is. When I create the swap chain, I'm going to get the swap chain itself, as well as a handle to the list of images which were created by the swap chain, for the swap chain, as well as I'm querying other things, so I'm going to get those as well at the same time, might as well. So the format and the extent. And this is the full set of things that I'm going to return from this create swapchain function. Okay, so here's what we've got so far. Very satisfying because we're using all the functions that we created. Also, we saw before that we can support 2 images at minimum. Okay, so I'm going to go 2 plus 1. The reason for that is that will give our engine a little bit of slack. Well, not even slack, right? It'll give it a little bit of juice that it can. We can have. We can speed things up. Now I know what I was saying about like, well, we can have 2 images and we still get like uncapped frame rate, but having 1 more image on the swap chain just gives us extra capabilities to be rendering 2 images and presenting at the same time, basically. So it's like we'll have 2 images, one we're rendering to, one we're presenting, and then we'll have another one just in case, so we can keep moving quickly. Okay. Enough of my word salad. So now what we're going to do is we're going to create the swap chain. And in order to do that, we'll need to populate a swapchain create info structure. So these are all the fields which are inside of that. And, sorry, this is a HPP definition. It's fine. It's fine. We're basically going to work with that. So what we'll do is we'll have create info. And then there's a bunch of fields that we need to set here. Structure type, S type, we don't need to set that. That has a default. P next, we don't need to set that. That has a default as well. Flags has a default of none. That's fine. But some things we do want to set here. So surface, and I like to use named keywords here. Little tricky here. Remember, format has 2 fields, format and color space. So I'm just going to go with that one. Image array layers will go 1, and then image usage. So the next one here is image sharing mode. And this is something we need to check. So sharing mode is basically saying, will this swap chain be used by just one queue family or multiple queue families? So what we can do is we can query this with find queue families. And what we're checking is whether the graphics and present have different indices or not. If they have different indices, then this is concurrent sharing mode, because it will be, the swap chain will be concurrently used by 2 or more different queue families. In this case, we need to specify how many queue families are using it and give a pointer to the queue family indices that will be using it. This helps Vulkan out. Otherwise, it will be exclusively used by 1 queue family, and we do not need to set these parameters. Anyway, so then we can literally just read it off from above. Okay, great. What do we have then? We have pre-transform. Okay. And we'll go with the identity. Actually, let's not do that. Well, because we already have this, right? We'll go support. But supported composite alpha could have multiple options. So we'll just go okay. Cool. Cool. All right. So that is our create info fully populated. The next thing we'll do is we'll create a bundle and we'll put these things in. So we'll say bundle. And again, we need to query this. So we'll say based on a logical device, looking for that function there. We'll query that. Then we'll call it. So go logical device, create info, and memory allocator, which will be none. We'll use the default. Okay. And I'm getting tired, so I'm going to copy paste. Okay, so then we need to get the images. So get swapchain images needs to be queried from the device. Then we can call it. Then we'll also store the format and the extent, and then we will return that. Okay, great. Now let's use it on the engine side. So we'll pop over. And yeah, this is still in the device sort of area. So we'll go bundle equals. Okay, then we can grab the stuff. Okay, that's looking good. Great, so we've got all of those. Now we can run this, and I believe it should work. Oh, no, it doesn't, because I have misspelt things. Okay. Definitely wouldn't be the first time. Okay. Now, fingers crossed, we try again. Great. However, it's also best practice to destroy the swap chain. The swap chain is based on the device, so we'll destroy it before the device is destroyed. So we have this thing here called a destruction function, which I'm reusing for multiple functions. That's fine. Okay. Yep, so we just call that self-device, self-swap chain, and allocator is none. Great. Okay, so run that again, and it works. Awesome. So just to recap, in today's episode, we had a look through, we talked about what a swap chain is. We had a look at the various little data fields that make up swap chain support, present modes, color formats, image usage, and things like that. And we had a look at how to create a swap chain and destroy one. Okay, hope you had fun, and I'll see you in the next one. Bye.